Which one was that? Was that one of the last ones?
Yeah, it's the last two.
Yeah, I know. I
So figure 2.57, 50 ohm slotted coaxial air line.
We got 50 ohm coaxial lines. Okay.
It's a coaxial air line. I don't know if that is. Terminated in a short circuit and in an unknown load.
Yeah, all right, go ahead. Is this the picture one?
Yeah, it's gonna have a picture.
All right. And let me just see what the picture, I know this one I've done.
This one.
All right, so this is the short circuit. See that one, the first one like this?
Yeah.
So the short is at 5.5?
Yeah.
Here's what happens on these. This is an airline. They have a short circuit at 5.5. Is that meters or centimeters?
Centimeters.
All right, so this is from this end. This is 0. This is 5.5 cm. And then, go ahead. I better look.
Do you want bigger?
I've got my book up there. I just don't feel like grabbing. So it goes to 12, no, 10 there, right?
Yeah.
That's 0. And this is where the short is? There's a short circuit, it goes to this. And then, all right, so here's the deal, guys. They say it's an airline, and this goes, they have a plot, it goes to 0 right here for voltage. Is this voltage, right?
Yeah, probe voltage.
Yeah, it just means the voltage. So here's what they're doing. They're measuring the voltage between here and here when there's a short circuit here. Y'all follow me? Now, there's a couple things. He's going to give you the frequency.
Yeah, he does.
What is the frequency?
Oh no, it says actually determine the frequency. No, he defined it.
All right, it's an airline, right? The
Yeah.
speed is probably
We also need
speed of light. So now you got to figure out from here. Oh, I'm sorry. From here, you get the frequency from that graph that goes. I'll try to just sketch this. Help me out here. They've got something that does. Let me erase this and try to do a better job of this. They got something that looks like this. Tell me if I'm close at least. Something like this, right?
It's more like there's a bounce and then there's one like.
Yeah, I know, but this is the first one, right?
You can just
See? All right, it goes. Starts at a high point. Just leave it there for 1 second. Let me try to get this better. Starts at a high point, goes to a low, goes back up to a high, and then goes to a low and comes up a little like so, right?
Yeah.
Basically like this. Then there's a second one, and it hits a peak at 9, and hits another peak somewhere about 2, and it does this. And this is the one that goes like this. Right?
Yeah, it's the bottom of 5.5.
Something like this and comes down. All right, now, here's the deal with these things. I want you to listen to me. Remember how he said every half wavelength, everything repeats? Y'all remember that? Mm-hmm. Look at that probe voltage. You see, and this isn't drawn well, but there's like a peak here and a peak here. And you can see that the one that goes like this. That's the one that the load's connected. The reason is because when it's a short circuit, it's going to go to 0. Do y'all follow me on that? It has to the voltage. We know this is the one. It's either a half wavelength away or it's right there. But from here to here, you get the wavelength over 2. It's half wavelength. Do y'all follow me on that? I mean, because it's from crest to crest, those are half wavelengths. I mean, anytime you're talking about the voltage on a transmission line, anytime, and you take a look at just magnitude of the voltage versus Z. Let me do it this way. Remember, V of Z itself is some V0 plus, and it's going to be e to the minus j beta Z plus reflection coefficient e to the plus j beta Z. Do y'all remember that?
Yeah.
Now, if you look at this, the peak value is going to be, when the magnitude of this is going to be 1 plus magnitude of gamma L times V0 plus. The minimum value is going to be exactly a quarter wavelength from that point. We'll go to a minimum. Smith chart will tell you. But here, what this will do, it'll always do this. If we just plot this and take the magnitude of it, it'll do this. always. And it'll go on forever. Now, from here to here, if you take a look at this, that would be y'all see how it's repeating from here to here, and you could go from like here to here. Y'all see that? That would be the distance over which it repeats. It'll be exactly half wavelength. So that's a half wavelength. So it's lambda over 2. Now you're going to have to estimate this. Take a look at that. And what do you estimate the distance is? Let me just do it here. What do you estimate this is the distance? You got to go from here to somewhere around, I think, 8 or 9, and then down to about 2, right? What is it about?
Yeah, it's about 7.5 centimeters.
Yeah, it's about 7.5.
What?
All right. So that means, now listen, lambda over 2 is 7.5 times 10 to the minus 2 meters. Do y'all follow me on that?
Yeah.
That means lambda itself is going to be twice that, or 15 times 10 to the minus 2 meters. Y'all with me? Now, this is an air line. It means it's moving at the speed of light. Y'all follow me? So if it's moving at the speed of light, then if you think about wavelength, that's equal to 2 pi over beta, right?
Yeah.
I'm just going through some of this. You're going to see this becomes very obvious. And since it is lossless, remember gamma is equal to alpha plus j beta, and that's square root of j omega L times, oh boy, since it's lossless, it's just going to be equal to j omega square root of LC, and I didn't cover this in class, did I? Since it's air-filled, the velocity is the speed of light. Did I talk about the speed of light? I remember. Velocity is speed of light. It's 3 times 10 to the 8 meters per second. Now that's telling you that's what it is. And does everybody know the speed of light in here?
Yeah.
From physics and stuff. So that's the speed of light in the vacuum. It says it's air-filled. It's effectively that. And because of that, without spending too much more time on this, when you deal with lambda, you might as well just do it this way. If it's air, just write this down. It's c over f. It's the velocity if it's air-filled. I'm going to modify this in a second to show you how to get it if it's not air-filled. You all with me? In his book, he says stuff and he doesn't go through the proof and show it because it comes later in the course. What he does is just expound. It says this. So the speed of light is equal to, it's approximately 3 times 10 to the 8th meters per second, and the frequency, well, if that's the speed of light, and we have the wavelength is 15 times 10 to the minus 2, right? So we want the frequency, it's 15 times 10 to the minus 2. You can see that the actual frequency itself is going to be 3 times 10 to the 8th, right? And it's divided by 15 times 10 to the minus 2. And what is that going to be? That's 3 over 15. It's 1/5 times 10, and this is going to be to the 10th power. So that's 2 gigahertz, isn't it, class? Is that the frequency Dave has? Any answers?
I don't have the answers.
Did I put the solutions up?
Yeah.
I can pull them up real quick.
Or it's with you put the whole chapter 2 and with homework 2, and so it's in that, yeah. I just don't have it pulled up.
Can you tell me what it is, sir?
Give me a second.
Anybody?
He's
It's
pulling
pulling
it
it.
up.
Okay. Do you have it
It's
too?
chapter 2.
Yeah, I'm
Because I don't know it off the top of my head. I think it's 2 gig.
yeah, I put it in my calculator.
Is it 2 gig?
I
Yeah.
can't get the.
But again, you're eyeballing the wavelength.
Yeah.
It could be right, could be wrong. You with me on that, class? So that's the frequency. What else does he want?
Was it
Viswar.
2.32?
A Viswar? All right.
When the load is attached.
All right. So here's the one with the load is attached. Is this guy?
It's 2.
Squiggly. Tell me the max value here. What's that? 8 or 6?
Or wait, no, it's
It's
2.
about
that.
the max is about 2.
Yeah, 2 meters.
Right here for this one, the one that.
Well, it's more like
Close enough.
Yeah, I know, but what is it? What I'm really saying is, if you look at ours, it does this, right?
Well, it starts out going down. It doesn't.
I don't
peak at
care,
the
but
beginning.
what's the maximum value of that
8.
one? What, 8?
Yeah.
You all with me? Is that 8?
Yeah.
Take a look. All right, so we got 8 is the max. Remember, VSWR is what? VSWR is just equal to Vmax, right? Over Vmin, right? So the max, you say, is 8. What's the min?
4.
4? Is it about 4? Now again, this is one of these things you're going to be approximately right, because some of it's based on how good your eye is, so it's over 4. What's the VSWR? 2, right? Isn't that right?
How'd you do that one more time? You said
Take a look at where the minimum is.
Vmax
Look
over
at your
Vmin.
book. Look at your book here. You got it in your book?
Yeah, it's just the.
Where's the minimum value? Right there. Is that 4?
Yeah.
What's the maximum value?
The maximum value is 8
10.
here.
About 8, right?
10.
It's 10 over there.
It's 10.
Oh,
Yeah.
oh, okay. 10.
10 over
Because
My bad.
it starts at 8 and then it goes maxed out at 10.
So this is 10, my bad. So that's 2.5. I'm sorry about that. You agree with that, everyone?
Okay. Yeah. That makes sense.
Before we go on, let me ask you this. How do you get the magnitude of the reflection coefficient? Just magnitude. Now that I have that. You remember? Anybody? This is a typical question on a quiz.
It's gonna be.
You got VSWR, right? What is VSWR equal to? Remember, think about this. The maximum value that can have is 1 plus magnitude of that gamma L. What's the minimum? 1 minus. So that means that what? VSWR, I'm going to show you this, is equal to 1 plus magnitude of gamma L over 1 minus magnitude of gamma L. What's gamma L? Well, didn't we do this one? I thought I did this one. How do you get it from VSWR?
Just go backwards as far as like.
And what would it be?
It'd be that equals. Hold up. I think we proved this.
What is it? It's VSWR minus 1 over VSWR plus 1, isn't it? Try that. So that's, I don't know if they ask it, 2.5 minus 1, that's 1.5 over 2.5 plus 1 is 3.5. So that's 1.5 over 3.5. That means the reflection coefficient's magnitude is what? Divide top and bottom by.
0.43.
Pardon me?
Wait.
Yeah, it's 0.43.
Yeah.
Is that right?
Yeah, that's
So 15 divided by 5 is 3. 35 divided by 3 is 7, right? 3/7 is that? Right?
yeah.
Point, what'd you say?
I said
0.43.
All right, do y'all see how to do it though? And here's how I got it. I know this equation, right? I did this last class. If you multiply both sides by 1 minus gamma over here, then I have to group, right? To get gamma L, I have to get the gamma L on one side, so I have gamma L here, and then it's going to be minus, and if you do it right, it's going to be, it will be the VSWR minus 1 over VSWR plus 1. But we proved that last time, didn't we? Yeah. How many? You all see this, guys? All right. What else is the problem asking? That's a good.
Lastly, it asks for load impedance.
All right. That's a good one. Okay. So, pay attention to this one. Now, here is where the load is, because that's where the minimum voltage occurs. He's giving you a snapshot of this line near the end of the line. But here's where the load's attached, because when they put a short in it, it goes to 0. It has to. Do y'all remember? Now, if that's where the load is, now when the load's put back in, it's this graph, right, that I try to estimate. If you look in your book, you're going to have to just, and I'll show you this too. So how do you get the loaded piece? If you look right there, that's where it is, right?
Yeah.
Now, where's the maximum from the load? And I'm going to draw it on a Smith chart so you'll see this a little better. And I'm going to take it easy and take it slow. I'm going to erase this stuff. I'll put it over here. Watch this. This is cool. You're going to like this with the Smith chart, because then you really see some of the things you can do so quick with the Smith chart. With an equation, you can do it. It takes some time. All right, so if you have a Smith chart, remember what I told you with the Smith chart? That's the first point, right? And I told you if you have a given load impedance, you have to do an arc around here, right? And I'm going to just go. So there's the load. Where does the maximum value of voltage occur? Remember, this is wavelengths towards generator, right? When we go in this direction. Here's my load. I don't know where it is. It could be up here. It doesn't matter. But I know when it comes through here, what is that point? The length from here to here? That is the viswar. Do you remember me talking about the voltage maximum? It is the viswar right there. All right, now, what is the viswar? 2.5. You agree with that?
Yeah.
You with me? So it's saying this point right here, or the distance from here to here, this is the point 2.5. And if you have a Smith chart, get it out and you can get your straight edge and protractor or compass and you can see this. And make sure you have a compass and a straight edge for the quiz on Friday. With me? So now take a look at this. Y'all see where 2.5 is? Do you have your compass? Go ahead, go from the center of the circle and just scribe that as such. Go ahead, take a moment to do this. I want to make sure you guys see this. This is cool. I don't know what he does in the book, but this is the way you do it. Do you have a Smith chart?
No, I didn't print
All right.
I have some extras.
that. Okay.
Do you have a straight edge and a compass or not?
No.
Oh man, please, from now on, always bring a straight edge and a compass.
You can
and
just
Smith-
get them. They're in the students.
Okay.
And you pass it. Thanks.
I don't have.
Where
Do
are
you
the
have one?
students? Oh, well, not the students there. Sorry, Haley. Sorry.
Hey, Ben Haley.
All right.
Yeah.
Now,
In the student store in the basement.
that bookstore. Yeah.
Okay.
You see the 2.5 there? And make a circle. Now, follow me on this. Here's where the load is, right? If we went away from the load, the maximum is, where is it about? I don't even know. How far away from where the load is? The load is at what? 5.5 centimeters? How far away is that maximum value? Take a look at this thing. You know what I'm talking about? Take a look at the graph for a second. Oh, you don't have a Smith
I
chart?
have a graph right here,
All right, take a look. From here, where's the maximum voltage?
up top, 14. Or
Well, it's actually back here, but let me look at it, mine. Oh, yeah. Here's how I get it. What page is that on?
111.
Yeah.
All right. So here's how I'm going to get it. I'm going to erase this so you guys can see. I want to draw this a little better. You won't be able to see. This is a cool problem, by the way, because it makes you think about all the applications of this. So we know the load is at 5.5 centimeters, right? Here's 0. Don't worry about the rest. That's where the load is. Now, if you look at this thing, you'll see that when I'm drawing, I'm trying to show you not the place. I know where the load is because that's where the short is. I'm trying to show you approximately what it does. It has a peak at about. Is that just shy of 4? It looks like if this is 4 centimeters here, it shows that the peak is about there.
Yeah.
It's doing this, right? And it doesn't show where the other peak is, right? You all with me? Now, I told you it repeats itself every wave or half wavelength, and the wave that would be 7.5 centimeters. Do y'all remember that? Mm-hmm. So look, it's here at 4 centimeters. So when I move this way, add 7.5 to it, you get 11.5 centimeters. It's off the page. Do you all see that, class? All right, so what is this part? Is this like 10 or 11 here?
The very edge is 10.
All right, so this part's off, but this is going to be 11, where the peak is at 11.5 centimeters. Now, we're here. Here's where the peak is. If we're at the load and we move, this would be wavelengths towards generator. You all follow me? We're at the load, wavelengths towards generator. The peak is 11.5 centimeters away. It was 11 centimeters, right? Just listen to me. That's where the load is, right here. I mean, at 5 centimeters. So if I take 5 centimeters and subtract it from 11.5, I get what? 6 centimeters, is that right? Let's see, where is it? All right, so I get 5 from 11 to 6, right?
Yeah.
That means the distance from here, where the load is, to here is 6 centimeters. You follow me on this? 6 centimeters. Now follow me. 6 centimeters. So how many wavelengths, or what fraction of a wavelength is that? You all hear me? I have to move from the load, that's where the load was, because we saw the short circuit. When they replaced the load with a short circuit, that's where it is. You with me on that? So I know the load's there. Here's the VISWAR for the actual measurement with load. To get from the load to this point, I have to go 6 centimeters. In terms of wavelengths, what is it? It would be 6 centimeters, and the wavelength is 15 centimeters, right?
That's 2/5.
What is that value?
2/5 or 0.4.
0.4 lambda, you might say,
Yeah.
or 0.4, all right? 0.4 lambda. Now in your Smith chart here, the load's somewhere up here, right? I have to go a total of 0.4. Now listen to me now. Wherever the load is, I have to move 0.4 lambda until I hit here. Do y'all follow me? Now just that. So if I start here, I know that this point right here corresponds to this point. I'll just call it A, and A, right here. So I have to go, and I have to reverse it. I have to go back for 0.4. Do y'all follow me? 0.4 wavelengths. Now if I go all the way to 0.5, I'm back at the same point. So I'm about here, and the distance from here to here is going to be 0.1 lambda. The distance all the way from here to here is going to be, well actually, no, sorry. From here, right here, to here is going to be, this whole distance is 4/10, so this is 1/10, so just hear me on this. You got your circle, I mean you made a compass, or circle, right? I don't know if he does it this way in his book, but I want you to see this. So, if you back up, or if you add, you could add just a 1/10 here. This is 0.25. You all see that? 0.25 lambda wavelengths to each other. This right here will be 0.25 plus 0.1, or it'll be 0.35 lambda. Can you see this point? This would be wavelengths towards generator. Everybody see that point? All right, now, what's the value here, real and imaginary? The normalized, that will be the value of the impedance, but I don't know what it is. What is the normalized load impedance? I'll show you.
Which you got a straight edge, but it's
Guys, make sure you bring straight edge, compass, and Smith charts to class.
I got about straight edge. Nice, thanks.
You got a compass, all right?
Yeah, I do.
Okay. This is a good problem. It brings out all the stuff you need to know.
Yeah, it's close to about 0.9
Almost 1 then.
minus J.95-ish.
Okay. About that, guys? You don't have a straight edge or compass, huh? All right, you with me, class? Please make sure you bring it. It really will save you a lot of anguish, because this stuff gets really crazy. All right, so that's the normalized, right? It's a 50 ohm load. The actual will be that times 50. What do you get for that? It's going to be what? Well, 4.5 roughly, right? Or am I wrong? 45.
45 minus 47.5, or yeah, minus J.
47.5. What does he have for the load?
50 minus 8.5, 48.
All right, we're close. All right, I'm going to, instead of 50, we have 45. Instead of minus J, 50 does he have? Or
He's 48.
All right, 47. But the reason is probably just the inaccuracy of our methods. All right, you need sharp pencils, good compass, good straight edge. If you don't have them, you'll foul these things up.
So will you have like tolerances for the gradient?
Yeah, I always give you a little stop. But I have to see what you're doing on Smith charts, and always label your points 1, 2, 3, 4.
Are
Now,
oh, sorry.
Go ahead.
Are the Smith charts going to be on the paper of the quiz?
Bring them.
Or
I'm
we bring
giving
our
you the latitude to bring your own Smith charts, so you print them out. That way you'll have you'll have the ones you like. There's so many different forms, but I like as big as possible. Like the one I sent, is that the one I sent you guys?
Yeah.
That's a good one. The Black Magic Smith charts are smaller. That one's pretty good. If you got a good printer, you get a nice resolution on that. It's easy to do. But you all follow me on this? Now let's go over this from a different span. This is reverse engineering, right? I did it in reverse the way I told you to do the Smith chart. Suppose we had the load, and we'll do the exact load. Now just follow me. We're going to do this whole thing. So we had a load here, and we have 50 ohm line, and Z0 equal 50 ohms. And the load was, what did we calculate it to be? 50 minus J48? Is that what Whitmer's book has?
Yeah.
50
minus J48.
Yeah, I'm sorry.
So it's 50 minus J48. Get your Smith chart. This way you'll see it all. Now we're going to start with, I'm giving you the load and I have Z0. Well, what are the steps you take? We're going to do this and you'll see all of them. First step is normalize ZL, right? Normalize ZL. Get this out of here. We're going to do the whole thing going the forward direction because this problem's pretty cool. It really shows you everything you need to know about these Smith charts. Not everything, but a lot that you can see. So we're going to go ahead and get the standing wave ratio, get the reflection coefficient. We're going to get several things that we're given, all right? So to start there, first thing is always ZL, which is what? The actual load impedance minus Z0. In our case, what will it be? It'll be 1 plus J, what is that going to be? 0.97 or 98, something like that? What is that? 48 over 50? 96, 0.96, right? Is that right, class?
Yeah, 0.96.
Yeah.
0.96, right? Okay, that's the normalized impedance. Now get your Smith chart. Do you have a Smith chart or not? Can you give him a Smith chart, please? You need these things. Do you have a straight edge? You do? Do you have it with you? You do? Do you have a compass? Okay, well, I want you to try to follow me on this one, because you'll see. Remember, we went the opposite direction. We went reverse. We were given some measurements, and we use a Smith chart now to figure out what's going on. Now, if you look at the Smith chart right here, here's the 1 circle. I always try to put that in for reference. And then this is J1, and this is minus J1. We have to find this point, 1 plus J.96, right? Well, I drew the 1 circle, right? J.96 is just about here, if you look. So your first point here would be, this is where you come in, ZL. You all follow me? All right. Now you take your compass, and now you go from here, dead center to this point, and you do this all the way around. I'm not drawn to scale, but you get the idea, right? All right, with me? Now, take your compass and look right at this intersection point. What do you read there?
About 2.5.
Everybody, you all see that? That's the VISWAR. So the VISWAR is about 2.5. It's actually probably exactly 2.5, as before, right? We got that from that, but I'm showing you how to do it. Forget that. I gave you a load on the cheat. We got the VISWAR. Now, take a look at your Smith charts, estimate this. On the bottom of your Smith charts, you have something, and this distance from here to here, if you measure this distance, I'll call it D. Really what this is the magnitude of reflection coefficient. Now you go down here, and they're going to have something called REF of E, that's the voltage reflection coefficient. And if you measure it, right, if you take this distance and bring it down here, now you'll see the magnitude of the reflection coefficient right here. Can you all do that? What do you get for your reflection coefficient? Doing it on the bottom. All right. Man, that's a light one. You gotta make them a little.
I'll print out another one.
Y'all with me? What do you get for it? Just measure it. Do you have a straight edge or not?
No, I borrowed his.
Just make sure you see how to do it down there. Now remember, the reflection coefficient If it's the whole circle, half of the diameter, then it's gonna be, what is it?
It's about 0.43-ish.
Isn't that what we got before?
Oh, yeah, yeah.
Yeah, we got.
Yeah, sure. Now you get that, so you know that the reflection coefficient is about 0.43, right? You can do it with the,
Yeah, you just draw from the edge of the circle, tangent, straight down, straight, and it says reflection.
or you can measure the circle and just take the measuring distance and bring it down there and do it, but you're doing it an easier way. Okay? All right, next. You with me, everyone? Did you see it back there?
Yeah.
And you're okay with it? Now, after that, so how far do I have to go to get the voltage maximum?